of shallow interfacial flows.
That's right. Okay. Well, first of all, I must apologize for my clothes. Right, I haven't dressed for the occasion. I got here yesterday, but unfortunately my suitcase did not. So these are the only clothes I got, and bad clothes are better than no clothes, right? So, okay. So the topic of my talk is stability of shallow interfacial flows. That's actually based on a paper I wrote with my advisor. The full title is daunting, so I shorten it a bit. Well, let's look at the model. It's a basic model, so I have two layers of fluid bounded by solid top and bottom walls. I call my upper layer 1 and my bottom layer 2. Okay. I'm going to make all the basic assumptions. So I'm going to assume that the fluids are not viscous and they don't mix, and that the flows are incompressible and irrotational. The key assumption here is the shallow water assumption. So I'm going to assume that the separation of the wall is much less than the length scale of the internal waves. And as a result of this assumption, I have hydrostatic pressure, and I could ignore the vertical motion of the fluid. Okay? I'm not going to make her Boussinesq approximation here, right? All right. So, well, from first principle, so from Euler equations, and from appropriate boundary conditions, I get these 4 equations, and you may notice that I'm working with the vertical mean of U1 and U2 here. I've seen that in some papers, people work with U1 and U2 and just assume that they are independent of Y. But we don't need to make that assumption. Okay, all right, and P is the pressure at the interface. Now, we have 5 unknowns here, right? H1, H2, U1, U2 bar, and P. And we do have 5 equations because H1 and H2 are not independent from each other, right? I'm going to non-dimensionalize H1 and H2 in such a way that the sum is equal to 1, okay? Rho 1 and rho 2 have also been non-dimensionalized in such a way that their mean is equal to 1. All right, so 5 equations in 5 unknowns, but we want to work with fewer equations and fewer unknowns, right? So what are we going to do about this? We notice that if we add the first and the second equation together, so you get H1 plus H2, and you take partial of a constant with respect to time, so you get 0. And as a result, you see that the volume flux, and I'm going to call my volume flux Q, should be a function of tau or time only, right? Now, if I find Q prime, so Q prime as a function of tau, I get an expression that looks like this. For the purpose of this talk, I'm going to look at the cases where Q is constant. And if Q is constant, then I could work in an appropriate frame and say that Q is 0, right? And I like to mention a few cases where my assumption is correct. So the first is when there are walls on the left and the right end. Okay, so walls like so. So you have a box of fluid, right, and you allow the fluid to sludge. Well, it's obvious here that the volume flux must be 0, right? The second case is when you fix some conditions at infinity and make Q constant. The third one is a little more, well, it's not too hard, but it's more complicated than the first two. So it's when the system is under the Boussinesq approximation, and we work on a domain that is periodic. And why would that give Q equal to 0? Well, if you look at this equation right here, okay, and you make the Boussinesq approximation, so you replace rho 1 and rho 2 by the mean density, which is equal to 1 here, right? So you would get H1 plus H2. That's also 1. And so that term is just partial P with respect to X. And if you integrate the whole equation on a period, you get Q equal to 0. Okay? All right, so with this assumption in mind, so I'm going to let Q prime be 0 and Q be 0 as well. And if I go back to these 4 equations, and I'm going to subtract the first equation from the second one, and the third equation from the fourth one, and redefine some unknowns, like so, I would get a system that looked like this. Okay. I'd like to mention something about the new parameter R. So I non-dimensionalize my rho in such a way that the mean is equal to 1. So if I let rho equal to rho 2 minus rho 1 over 2, and you can check that it will be bigger than or equal to 0 and less than or equal to 1. If I assume that the fluid in the bottom layer is heavier, okay? So I get this system. And it's actually a good system if you are not going to do anything to R. But we want to do something to R. Because the way we define R, we would hope that if you let R go to 0, then you would get the Boussinesq approximation. And if you look at this system, that's not going to happen here. Because if you let R go to 0, you would kill this term right there. And that's buoyancy term. And you know that when we make the Boussinesq approximation, you want to keep the effect of the density difference in buoyancy term. Right? So that system is not good right now for our purpose. Well, what do? We make some rescalings, this 3. And we have a system that looks like this. Okay? And you notice that I moved the buoyancy term to the left side of the equation now. And it's not affected by R equal to 0. Okay? That system will be our main system today. And I'm going to just call it system 7. Let's see what happens if we let R go to 0. We get that system, a symmetrically looking system. And it should not surprise us that if we go back, how do I go back faster then? If you go back to, let's see, that page. Yep. If you go back to that page and you make the traditional Boussinesq approximation with the third and the fourth equation, then you would get something like this. Okay, let's see. You keep the rho 1 and rho 2 in the buoyancy term, so you get this. And the same thing for the second equation, right? So if you do this and you go through the same process, then you should expect to get exactly this system. Okay, how do I do this? It's like you have to be very precise to get that pointing finger. Okay, all right, I got it. Okay, so that's the introduction part. Now, I'm going to study nonlinear stability of the full system, of system 7, but it's actually instructive to look at the nonlinear stability of the system with the Boussinesq approximation. So I'm going to look at system 8 first. You look at this system and you see that it's a quasi-linear system, right? So you can actually write it in the matrix form like so. Okay? U is a vector HW, and B is a matrix. Right? And it's easy to find eigenvalues and eigenvectors of B, like so. And this system is a system of mixed type, and you want a wave-like solution. So you want the eigenvalues to be real, and you want a complete set of eigenvectors. And that will happen when the absolute value of H and the absolute value of W are both less than 1. Okay. All right. Well, her system here is so simple that you can actually find more. You can actually find Riemann invariants. They look like that. And you can rewrite the eigenvalues in terms of R plus and R minus. You may wonder why I do this, and I will answer that question later. Okay? All right, so let me show you a typical solution of the system 8 up to breaking time. So what do I have here? I have H as a function of x and W as a function of x. And I also show you the plot in phase plane. So H versus W. Okay. My initial data is the thick curve, like so, and like so here. And I show the solutions at some points in time with other curves. Right? Like that. And the dashed lines that you see here are the boundaries of the hyperbolic region. It's just a square. Okay? All right, so let me show you another solution. But now I'm going to put the initial data very close to the hyperbolic boundary, like this. Okay. And you look at this solution, and you feel that the solutions try to avoid crossing the hyperbolic boundary. Right? So you ask this question, can a solution of the system 8 leave the hyperbolic region? And the answer is never. Never for any initial data inside the hyperbolic region. And I'm not making this conclusion by just looking at one picture, right? There's a theorem for that. Like there's an app for that. So a sufficient condition for nonlinear stability is a theorem in a paper I quoted at the end. So I call it reference 1 here, and it's actually written by a few of you in this lecture. It says that a quasi-linear system of mixed type is non-linearly stable if its eigenvalues are smooth functions of its Riemann invariants, and we know that that's the case, right? That's why I draw the eigenvalues in terms of R plus and R minus. Okay. So we got this conclusion that the system 8 is non-linearly stable. What about the general system? It's quasi-linear, so I can write in this form again. Here's dA, it's more complicated, but still I can find eigenvalues and eigenvectors. They look like so. Now, you will have a hyperbolic system if the absolute value of W is less than that function I call alpha of R and H, and it depends on R and H like so. Okay, let me show you what the hyperbolic region look like. It looked like the dash curve. Okay, so it has curved top and bottom boundaries, and I plot it in comparison with the hyperbolic region for the system with the Boussinesq approximation, which is a square. Okay, so you can kind of see that when H is close to -1, okay, so that means that the top layer is much thicker than the other one, right? You can see that the system can actually withstand more shear. Okay, so and you can also see by looking at this expression for alpha that if you let R go to 0, you get alpha equal to 1. So you get the hyperbolic region for the system with the Boussinesq approximation. Okay. All right. Now let's look at some typical solution of the system. A typical sloshing solution look like so. I don't know if you can see the thin curves clearly, but so there's something I like to say about this, but I'll come back if I have time to say that. Let me show you another solution. Now, I put my initial data close to the top and bottom boundaries, right? And what happened is that the solutions escape the hyperbolic region. And so the system 7 becomes elliptic and is ill-posed as initial value problem. And you can see this from the numerical oscillations there. Okay? Well, so we know that the system 7, the full system, is not non-linearly stable because you have initial data inside the hyperbolic region, but the solutions leave the hyperbolic region. Okay, could I have concluded that the system 7 is not non-linearly stable without finding this numerical example? And the answer is yes. Because there's another theorem in the second paper that I quoted at the end. It's a necessary condition for nonlinear stability, and it says that a quasi-linear system of mixed type is nonlinearly stable only if its eigenvectors are tangent to the hyperbolic boundaries. And it's not hard to check by looking at the eigenvectors that they are not tangent to the top and the bottom boundaries. Okay, so here's the key question to this whole talk. How far do we have to stay inside the hyperbolic region to guarantee that we never escape the hyperbolic region? To answer this key question, I need to introduce the notion of simple waves. And a simple wave is a solution in this form. So it's a composition of a vector value function and a real value function, u and theta respectively. Now, if you plug this expression back into equation 10, okay, I don't want to go back to that, so let me write down equation 10. It's this equation. So if you plug that expression back into this equation, you get an eigenvalue problem, right? If you want a non-trivial solution, you would want u prime to be an eigenvector of A, and you will want theta to satisfy this diffusion equation. Okay? So how do we construct a simple wave? Well, first of all, we go back and solve this equation right here for you, and then you pick some initial state for theta, call it theta naught, and then you either solve this equation for theta, and then you compose u with theta to get the simple waves, or you could evolve this equation right here. Well, good thing I wrote it down. From the initial data, which is the composition of u and theta naught. Okay. Whatever you do, either way, by construction, you should see that the phase plane representation of the simple waves always remain on the curve u. And I have an example to convince you. So I construct a curve u right here. It's kind of thin here, okay? And I put my initial data on that curve u. So that initial data is actually a closed loop, but it lies entirely on the curve u. And what happened is the evolution of the solution, but it always remains on the curve u. Okay? And since I'm going to use the curve U more often, I'm gonna abuse the language and use the term simple wave to call the curve U instead. All right. So how can we take advantage of the simple wave? Oh, well, let me show you something else first. So just to give you some intuition, let me show you some examples of simple waves for the system 7. I show you 4 examples here, right? This one, this one, this one, and this one. And you can check that the simple waves are tangent to the left and the right boundaries, but not tangent to the top and the bottom ones. Okay? How can we use the simple waves? All right, here's the key idea. So the key idea is that if the solution curves touch the simple waves, then they must evolve along the simple waves. And here's why. So let me draw a solution curve. Let's say like so. Okay. Right, and her curve is in the phase plane. So x-axis here and w-axis here. And if I look at partial of u with respect to x, so that's the partial of the vector hw with respect to x. Well, that vector has to be tangent to this curve, right? Say if I look at partial of u with respect to x at that point, it has to be like so. Now, suppose her solution curve touches a simple wave at this point, like so. Okay, then partial of u with respect to x here must be tangent to the simple wave. But we know that the simple wave is determined by an eigenvector of A. So that means that partial of u with respect to x is an eigenvector of A. So when you look at partial of u with respect to t, right, from this equation, partial of u with respect to t is minus A times partial of u with respect to x. It has to be in the eigenspace of A. So in other words, a partial of u with respect to t either points this way or that way. And as a result, the solution curves would move along the simple waves. Okay? Right. So that would be an explanation for a general situation. There's some technical issue that I might come back to explain later if I have time. All right. So from this key idea, let me show you what happened. Suppose you have initial data and you can bound it with simple waves. So I have this initial data right here. And I bound this initial data with 4 simple waves that are tangent to it. You would expect the solution to remain in this bounded region. And that's exactly the case. So if you evolve the system set of 7, you would get the solutions bounded in this region. Okay. On the other hand, if you cannot bound your initial data with simple waves, then the solution may leave the hyperbolic region. And that's what happened here. I have this initial data, and I cannot bound it with simple waves. So I show you an enlargement of that part here. Okay, you get one simple wave like this, and another simple wave like so, and you cannot bound initial data. So solutions could leave the hyperbolic region. Okay, but it's not always the case that if you cannot bound initial data, then solutions would always leave the hyperbolic region. Right? It could be that waves break first, and they don't leave the hyperbolic region. Okay. All right. We can do better than this. We can actually use simple waves to construct what we call the maximal stable region. So by a stable region, I mean a region on the phase plane where if you put initial data inside that region, then the solution would never leave the hyperbolic region. And I claim, so let me show you a maximal stable region for r equal to 0.5. I claim that it looks like so. Yeah, with the thick curve right here and here. So now let me tell you how I construct these boundaries. Well, on the left, we know that the left and the right boundaries are simple waves, right? So we know that stable region extends all the way from the left to the right. And then we know from symmetry of the problem that we could just find the top boundary of the stable region and then reflect it for the bottom one. Okay, so the top curve here, well, it's actually a simple wave, right? Because I know that if I put a simple wave there, then no solutions would cross the simple waves. And I can be more precise. So it's actually a simple wave determined by this ODE. Well, it's actually in the family of VA minus the eigenvector of A. And about the boundary condition for the ODE is that the curve here meets the top right corner of the hyperbolic region. If you look at this ODE closely, then you will see that it's actually singular at the top right corner here. So you have to do some local analysis, but you do get this curve. Okay, how am I doing? All right, let me go to the conclusions then. Okay, thank you. So we have done a few things here. We have found some appropriate scaling that would give a Boussinesq approximation by just taking R close to 0. We found that without the Boussinesq approximation, shallow interfacial flows are not nonlinearly stable. And we use simple waves to bound solutions of quasi-linear systems. And we also use simple waves to construct a stable region, which guarantee evolution in hyperbolic regions. All right. There are some other things I like to talk about, but I'm not going to do that. So let me go straight to the references. Okay. So the first two are the two that I quoted in the paper, and in the paper I quoted many more papers. So you must forgive me if I don't quote your papers here. Okay. All right. Question?
Some questions?
Yes, sir.
Can I hear more comments about your prediction of wave rate? Because the quasi-linear system that you derive is very similar to the Airy's nonlinear wave equation, which has full nonlinearity but no dispersion. Mm-hmm. And it's restricted always for small gradients.